So, very good afternoon. I be to Dr. Zaidi and everyone here present here today. So, the topic of our discussion is installation design project, which in this case, project C consists of Surau Canteen and Divan Scholar. So, allow me to introduce myself. My name is Jeevanjeet Singh, unlike Jasbinder Singh, and my fellow other teammates, which are Jemison, Anak, Lim Tiek Guan, Mohammad Riduwan, and Nickstanley Meridin. So, we'll further proceed with the next slide. So this is the table of contents. So I will be presenting progress 1, followed by Jemison by progress 2. Progress 3 will be presented by Lim Tiek Guan and Nickstanley Meridin, and progress 4 will be presented by Mohammad Riduwan. So we will proceed with the next slide. So as you can see here, progress 1, there's actually various steps that we need to do in order to do the lighting selection. So first of all, we have to measure the length and the width of the space, followed by calculating the space area, determine the height of the working area, calculating the room index, determine the coefficient of utilization from specification table, set the type of luminaire and its output lumens, and determine the lighting design lumen, determine the required illuminance level for the particular type of space from JKR specification, set the maintenance factor. In this case, we set the maintenance factor to 0.8, calculate the required luminaire in the particular space, and arrange the luminaires in the particular space. So instead of me explaining like this, why don't I present you an example? So there are several processes when it comes to designing the lighting components in the selected area. First of all, we need to identify the sort of space and the purpose of the space, measure each room and space in the building, for example, the AV room in Devan Scholar. So as you can see here down in the figure below, it's actually a screenshot of the delay AV in Devan Scholar. So its dimensions are lengthwise 2500 millimeters, in this case which is 2.5 meters, and the width about 2000 millimeters, in this case 2 meters. Why do we need to change it to meters? So that it's easier for us to determine the number of lights required, the number of luminaires required. So we'll further proceed. So we will calculate the room index of the filling room using the mounting height. So room index is equals to length times width divided by mounting height times by length plus width, where the mounting height of the luminaire is above the working plane, in this case the AV room. The room height is fixed at 3.5 meters. So where do I determine the room height at 3.5 meters? Is by referring to the side drawing of the SMK tender. From there, I can determine that the room height is about 3.5 meters. Hence, the length of ceiling to floor minus by the table height working area. So as you can see, the image on the right hand side, the general building areas, the selected lighting design lux table, I've decided to choose the store and stock rooms. In this case, the telecommunication board and switchboard room. According to JKR standard illuminance, the lux is about 150, where it's being measured on a horizontal keyboard. And also, its extra notes is to avoid specular reflections on boards. So how do I determine the mounting height? So 3.5 is actually determined from the side drawing, followed by minus by 0.7, where the lumen light is being reflected onto the cable. We get about the mounting height is about 2.8 meters. So how do I determine the room index? So by getting all these values, we'll substitute into the following formula. We get the room index to about 0.40. So next, we will see that the coefficient of utilization was calculated using a data sheet based on the plot type used. So in this case, the data sheet is YLI from a company called YLI, which is actually CRIM and JKR and ST approved. So the image on the left hand side actually determines the luminaire type, which is YBC236, which is actually mentioning fluorescent tube 2x36, which each lumen being each bulb in the fitting is about 3250 lumens. So the LOR here is actually the light output ratio, which in this case we assume is the efficiency, which is about 58.3, and the LMAX Candelas 949.2 is actually we didn't really utilize in this formula. So okay, so the lamp type chosen is YB6236 T8. Hence the lamp code is FL. The lamp code chosen is FL T8EXD36 fluorescent 2x36. And from the table, the room index is, when we calculated, the room index chosen was about 0.6, but is used because the K 0.4 is not in the table. So when we calculated earlier, we get the room index is about 0.40, but hence it's not in the data sheet. So we take the nearest value in this case, which is 0.6. Assuming we choose the brightest room reflection with 70% reflection in the ceiling, 50% in the wall, and 20% in the floor. The coefficient of utilization is about 0.24, as I highlighted here. K equals to 0.6 is equals to 0.24, and the maintenance factor, we assume that it's kept to about 0.8. The COU chosen here is actually according to JKR specification for easier for so that we have a uniformity when it comes to designing the luminaire. In this case, based on the data sheet, the SHR nominal is about 1.25. So how do we actually get the value is from the corner right, as I highlighted here below. So it's about 1.25 meters. So the SHR nominal actually determines the placement of the lighting. Where do we want to keep? Is it nearest to the wall, or is it further from the wall? Anything below, then the SHR nominal value is assumed to be suitable. So the lumens, hence we calculate the lumens. We get about 2 times, because 2 times 36. So we get 2 times 3250. The lumens about 3250 for one lumen, times by the efficiency, we get about 3789.5 lumens. And then the average luminance according to JKR specification due to AV room type of working area is about 150 lux. And by using the lumen method calculation, the number of lamps is conducted to estimate to exact the quantity of lamps. In this case, by substituting the formulae, we get about the number of lamps required is about 1 lamp. So the actual number of lamp is 1, but we must also consider the configuration of placement of light being placed in the area so that the full room is fully illuminated. In this case, I have actually placed it in the center to ensure uniform lighting, so that the light is being reflected on table and the user can see it much more clearly and more efficiently. So this is actually one example. So how do we repeat? So hence the following processes are repeated with the following areas as shown in the Excel table. I'm not really sure if you all can see the Excel table, but the same process is actually repeated for each consecutive room with respective to their values from the mounting height, the area room index, COU, the lux value, the maintenance factor is kept constant, and then the lamp type is determined, and the lighting design lumen, followed by the actual lamp quantity and the quantity of lamps used. Its rated wattage is SHR, as I mentioned earlier, is the placement depending on the lamp arrangement, and it's also starting from the wall, meaning that we are placing the luminaire, the distance between the luminaire to the wall, and then the SHR value here is actually based from one luminaire to another luminaire. So that is all for me. So hence I will proceed with Jemison to further give his explanation on progress. Thank you.
Hi, my name is Jemison. So in this part, I'll be presenting about Progress 2, which is about low flow balancings and energy sinks. Progress 2, we are required to provide distribution board for lighting, fan, power socket, and air conditioning with a balance loads. The first one is the load estimations. We are categorized it into three, which is for lighting, fan, power socket, and air conditioning. So the loads for lighting, we can refer to Progress 1. While for fan, we need to design it based on the type of fan we are using. While for power socket, we have two types of power socket, is 13 amp and 15 amp. Air conditioning, we need to design it as well, so we need to calculate the required horsepower to be used in the area. So how to calculate air conditioner horsepower is area multiplied by cooling factor divided by 9,000, then we will have horsepower required in the building. So for the DB type, since we are using three-phase system, so we will have options for 4 ways, 6 ways, and 8 ways. For example, here we are using 8 ways, so we have total of 24 circuits we'll be using in the DB, which is contained with red, yellow, blue phases. Next, for the total connected load, in order to have with the connected load, we have to know the quantity of the load will be used in the DB with times with the connected load. So connected load, from here we can see for the lamp type for fluorescent lamp, which have 36 watt. So in the connected load, we have to add 6 watts because of the ballast. So while for LED, it will be the same as the stated voltage, which is 1.2. The same will be used in other DB for socket and air conditioner. So third one is for maximum demand. In order to have maximum demand, we need to have diversity factor. So from here you can see the JKR diversity factor table. So for example, we are doing in the canteen. So for lamp diversity factor for lamp and fan is 0.8, while for socket 0.4, AC 1, water heater 1, isolator 1, and the others also need to be referred to the tables. So from the diversity factor that we have, we need to multiply with CI that have been calculated. So from after we estimate our load, we can do the load balancings. But before we do the load balancings, we have to calculate the rated current for each load. From here, you can see the calculations is maximum demand divided by 230 times with 0.8 of power factor. This is for the single phase system. So for three phase system, it will be the same. Just that it will be divided with 3 times with 400 times cos theta. Once we have our rated current for 3 of the phases, we can calculate for the load balancing, which is we have the allowable range, which is within the 50% margin. So in order to calculate for the allowable range, for example here we have red phases, with minus with average current, calculate here, divide by average current, and with 100%. Then we have our allowable range. This will be repeated for yellow and blue phases. So this is the result from the calculations, which is our system have 6.50, which lower than 15% HRS. So it is can be used, which is mean that our load balance. So this is the example of our Excel for load balancings. We have red, yellow, and blue phases. Number 5, we have we must design our MCB rating. So the MCB ratings for lighting and fan is 6 amp, power socket 16 amp, and while for air conditioning is 32 amp. This will be fixed for our MCB. So you can refer to this table as well for the MCB ratings. Next is about cable size. Cable size, we are required to design it for lighting and fan is 1.5 mm. For socket is 2.5 mm, while for air conditioning is 4 mm. This cable size it will be further discussed in the progress 4. So I will show you about the AutoCAD drawing for lighting and fan. So we have to draw lighting and fan in the AutoCAD. Also, the DB will be placed in the billet switch. Next, this is for the power socket as you are loading. So we are required to draw sockets and design it in the building in the AutoCAD. For the DB also will be placed in the billet switch. Last one is for air conditioning at the day 1. So we are designing the air conditioning and draw the air conditioning in the day 1. And the DB also will be in the billet switch. That's all for me. Thank you.
Hello, my name is Nickstanley Meridin. So let's continue to the progress number 3. So in this progress number 3, we are focusing on the distribution system. So here we will design our schematic diagram using AutoCAD for the MSB, SSB, and the DB. And the last one, we will design our power factor correction for the MSB lah. So let's go through to the next slide. So this is the distribution system from MSB to the load. So as you can see here, incoming from TNB will go through to the MSB and then divide into 3 SSB. So in our design, we design 3 SSB, which is SSB Day 1, SSB Surau, and the SSB Canteen. And then we go to the DB lah. Then as you can see here, we put a meter for the entire system because we want to know how much the cost, RM cost, for the entire system that we design. And also we put the meter at each SSB because we want to also know the cost for the each SSB lah. So let's go through to the next slide. So this is the MSB single line diagram. So as you can see here, SSB Day 1, SSB Surau, and SSB Canteen. For the SSB Day 1, we use MCCB 120A and then 4 pol. For the Surau and Canteen, we use MCCB 50A 4 pol. Kenapa kami menggunakan 4 pol? Why we use 4 pol? Because we want to isolate our neutral, so we don't want to isolate just for the red, yellow, blue only. So it's I think it's very safety instead of we use 3 pol. So let's continue to the next slide. So as you can see here, this is the perfect decoration, but we'll not discussing at my part. So let's continue to the next slide lah. So this is the SSB. So incoming from MSB, so we have 5 DB lah. DB lampu 1, DB lampu 2, DB 3 soket, DB 4 soket, and then DB 5 aircon. So each DB, we connect it to the MCCB, which is we use 20A and 4 pol. Okay, seperti yang kamu lihat ni lah doktor. So let's continue to the next slide. So this is the next slide. So this is the single line diagram for the lightning DB. So yeah, for the lightning we use RCCB. Sensitivity value is 100 mA. For the socket 30 mA. For the water heater 10 mA. So let's continue to the next slide. So this is the single line diagram for the socket. Then let's go to the next slide. Okay, this is the single line diagram for the aircon. Why we use single phase? Because when we calculate the MD, the total MD for this DB are not exceed 10 kilowatt, 10 kV. So when we read at JKR or TNB document, we find it when MD tidak melebihi 10 kV, so automatically kita akan menggunakan single phase system lah. So tapi kalau lebih daripada 10 kV, automatically kita guna 3 phase lah. So in our case, our MD is not exceed 10 kV, so we just use single phase lah, because here you can see we have just one icon, so it's a very problem to us lah to make load balancing when we use 3 phase system. So that's why we use single phase diagram, and then also you can see the TNB document here. Oh, okay. This is the TNB document. So 12 kV maximum demand. So single phase lah. For the 3 phase, ya up to 12 kV lah until 72 kV maximum demand dia. So that's it for me. Thank you.
Hi, my name is Lim Tiek Guan. For this assignment 3 progress presentation, I will focus on the design of power factor correction board or PFCB. The objective of this part is to improve the power factor of the electrical system in our proposed building project. Okay, this is the main switchboard MSB layout that integrates the power factor correction system. The PFC unit is connected in parallel with the main bus bar to improve the system efficiency and reduce the penalty due to the low power factor. Okay, here is the lot list for the canteen building. It includes the connected lot in both watt and ampere for each room. For this data, we can calculate the total maximum demand and the total connected lot. This value help us select the proper rating for the MCCB and the RCCB, including the correct milliamp sensitivity for the protection. Okay, for the all three buildings, the Surau, canteen, and the school, the total maximum demand is 100,000 and 223.98 watt. Based on this, we choose a 225 rating amp and backing capacity 50 kilo amp MCCB to safely handle the total load and ensure the short circuit protection. Our system aims to improve the power factor from 0.75 and to 0.95. We use a 525 watt rated voltage capacitor bank. From our calculation, the existing reactive power QC is 55.446 kilo VAR, and the required new QC is 88.85 kilo VAR. We apply a set state switching sequence of 1, 1, 2, 2, 4, 4 using a micro power factor regulator. Atop the calculated single capacitor size is 6.35 kilo VAR, but we choose the nearest available rating, which is 7.5 kilo VAR from the blend shower capacitor. So the total capacitor bank size we use is 105 kilo VAR. This is a schematic diagram of the PFC system. At the top, we have a 225 MCCB, followed by the set-state micro power factor regulator. Each stage control a capacitor unit connect through a 7% reactor and a 3-pole ceiling contactor. The connector and MCCB are sized according to the capacitor value from 20 amp and 32 amp for the small step and up to 60 amp and 65 amp for the largest one. That concludes my presentation on the power factor correction board design. Thank you.
Hi, my name is Mohammad Riduwan, and my metrics card is 221091065. Today I present the progress for cable solution for my group, which is cable solution for Surau Block and Yield. So the main objective of the progress for is to design a regular wiring system connecting the main switchboard, sub-switchboard, both of the operation, and in information for steps power distribution. For the second objective is cable solution. So we choose the cable for the sub-main cable SP1 based on the voltage shown and set these standards to ensure performance, stability, and compliance levels. Last but not least, it is the regulatory compliance to ensure that the electrical installation meet health, safety, legal, and environmental and cultural standard for transport. So this is a rating factor for cables. We use this formula IT more than or equal IN over CACC, CDCF, CGC, ICS, commas with our notation that we define the current
connection factor. So we choose number 1.00, and for the cable touching, we use the branch there in our surface impedance or loss reference. So this is the current ampere from distribution board to final load. From the formula I presented before, I think we managed to get our IN, which is 557 in here. So we choose the conductor cross-section area 10 mm per square. So to be informed that this is a sizing cable that we get for the DB accord from the surround. Okay, next we use the reference method 3 enclosed in conduit on the wall or in the trunking system, which is for the distribution board to final load, that we use 2 cable, which is 57 ampere, and that's how we got the 10 mm square of the cross section area. Next, I present the current ampere sub-switch board to distribution board using the same formula, but this time we change the 3 or 4 cable and 3 phase that inform that it is from SSB to DB. From the 3 or 4 cable 3 phase, we choose the 50 ampere, and we got the 10 mm square for the conductor cross section area. So this is a voltage drop from distribution board to final load. Don't mind that the formula we use is here, and this is the percentage of voltage drop that we get. Okay, for the voltage drop from distribution board to final load, we use the table 41A. For this, we use the table 41A, and we choose the 2 cables single phase from the reference method 3 and 4. In conduit, because we use the conduit method, we got the voltage. We use the 16 mm cross sectional area square, and we got the voltage drop, which is 2.8. Next, by using the same formula, we choose the voltage drop from SSB to DB. We calculate that, and by using the 16 mm square conductor cross sectional area, our voltage drop is 2.4 for surround block. Here's the data that we got for the surround block. They include the voltage drop, cable length, proposed cable size, our rating, our LD, next demand. This is the data surround DB to final load and SSB to DB. Okay, this is our distribution base for each phase. This is our conduit wiring system. We choose the rectangle system conduit. It is easy to connect all the air conditioning together. Okay, so the cable size justification, why we choose it, our cable size or the value. First, the PVC cables are used between sub-switch board and distribution. It is installed in metal trunking. Next, the SFP PVC cable are connected to the main switchboard to sub-switch board in the PVC panel and also routed through trunking. Why we choose the SFP as the PVC cable? Because it is used for long distance grounding, which is linked to surround and camping to ensure mechanical strength and durability. Next, for our surround voltage drop justification, SSP from the DB, which is the PVC cable, its average drop is 0.06%, and maximum drop is 0.10%. It is excellent for saving and it has a minimal loss. And then next is DB to final load. The voltage drop average is 0.79%, max is 1.117% for the 1 solar tower. That is slightly over single limit. The total drop is below 4%. And the single circuit is 2.5 mm square, which is 36.05 meter, and 6.0 mm square, 44.3 meters, really still below the compliance from the JKR. So the design compliance is, we use the design is stable type and size and length are considered by follow the JKR 66 factor, and means the voltage drop and safety condition set up by the JKR. In conclusion, we design a safe, efficient, and efficient and compliant electrical system for surround, camping, and D1 solar. We use PVC and SFP cables with conduit and trunking system for durability and safety. Adhere to JKR and IEC standard, we ensure that we got the minimum voltage drop and max hazard protection. Last but not least, we support scalability and energy efficient for long-term operation. That's all. Thank you.